Let me ask you something. What is 2 plus 2? You know the answer. Everybody knows the answer. 4. You learned that before you could tie your shoes, and you never once thought it was strange. But I want you to sit with that for a second, because 2 plus 2 equals 4 is one of the most dangerous ideas in the history of the world, and nobody ever warned you about it. See, here is what I mean by dangerous. When you say 2 plus 2 equals 4, you are not just counting apples. You are not just saying, I had 2 apples in my left hand and 2 in my right, and now I have 4. You are making a much bolder claim. You are saying that this fact, 2 plus 2 equals 4, is true everywhere. True yesterday, true tomorrow, true on the moon, true inside a star, true in a galaxy so far away that light from it has not reached us yet. You are saying this little rule that you learned when you were 5 years old is a law that the entire physical universe apparently obeys, and I want to know why. Because think about what we did. We made this stuff up. I do not mean entirely, obviously. We noticed things. We noticed that if you have a pile of rocks and you add another pile of rocks, you get a bigger pile. That is not mathematics. That is just paying attention. The mathematics is what came next. The symbols, the rules for manipulating them, the logical chains that connect one statement to another. We invented a language. And the astonishing thing, the thing that still gets me out of bed some morning, is that the universe appears to be fluent in it. So let us start at the very beginning and work our way up, layer by layer, because this gets stranger the further you go. Thousands of years ago, somebody in Mesopotamia wanted to keep track of how many goats they owned. Fair enough. You scratch a mark on a clay tablet for each goat. 1 mark, 1 goat. 2 marks, 2 goats. This is not deep mathematics. This is bookkeeping. Then you want to trade some of those goats for some wheat, and you need to figure out how much wheat you ought to get for 7 goats, and so you develop multiplication. Then you want to divide up a plot of land among your sons, and you need to figure out areas, and so you develop geometry. Measure the earth. That is literally what geometry means. Measuring the earth. And if that is all mathematics ever was, if it was nothing more than a sophisticated tally system, a tool we built to manage our affairs, nobody would lose a moment's sleep over it. You would say, well, of course, mathematics describes the world. We designed it to describe the world. We took it straight from the world in the first place. And that sounds perfectly reasonable. End of story. Everybody goes home. But something funny happened. The bookkeeping started doing things that had nothing to do with goats. Here is an early example that shook things up. The ancient Greeks were playing with geometry. They loved geometry. It was practically a religion with them. They noticed that if you have a right triangle, the square of the longest side, the hypotenuse, equals the sum of the squares of the other 2 sides. The Pythagorean theorem. Beautiful, you can check it yourself with a ruler and some graph paper. But then somebody, probably a student of Pythagoras, asked an innocent question. What if the 2 short sides are both 1 unit long? What is the length of the long side? Well, by the theorem, it is the square root of 2. And the square root of 2 turns out to be a number that cannot be written as one whole number divided by another. It goes on forever, without repeating, 1.41421356 and so on, never settling into a pattern. The Greeks called these numbers irrational, literally without ratio, and this horrified them. The Pythagoreans believed deeply, philosophically, religiously, that the universe was built on whole numbers and their ratios, harmony, order, proportion, and here was their own beloved theorem coughing up a number that was fundamentally disorderly. Legend has it that when a member of the Pythagorean school proved the irrationality of the square root of 2, they swore him to secrecy. Some versions of the story say he was drowned for revealing the truth. Whether or not that is true, the sentiment is revealing. The mathematics had uncovered something about the nature of number itself that nobody wanted to hear. Right at the very beginning, the math did not care what the Greeks believed. It had its own opinions. And it gets deeper than that. Because the Greeks also discovered that these irrational numbers were not rare curiosities. They were everywhere. Most numbers on the number line are irrational. The rationals, the nice fractions, are like scattered islands in a vast ocean of irrationality. The universe of number is at its core far wilder and stranger than the tidy system of ratios the Pythagoreans believed in. They thought they were building a neat little house of mathematics. They were actually opening a door into a wilderness. And the wilderness kept growing. Pi, the ratio of a circle's circumference to its diameter, turned out to be irrational too. And not just irrational, but transcendental, meaning it is not the solution to any polynomial equation with rational coefficients. The most natural number in geometry, the number you get just by drawing a circle, is mathematically untamable. It refuses to fit into any finite algebraic box, and yet it shows up everywhere in physics. In the equations for waves, for oscillations, for the distribution of heat, for the shape of electric fields, for the probability curves of quantum mechanics. A number born from circles is essential to understanding things that have nothing to do with circles. We will come back to that. All right, that is the first crack, but it is still just a crack. Let me show you something much more startling. Fast forward roughly 2,000 years, we are in Italy. The 1500s, the Renaissance. Mathematicians are dueling each other. I mean literally dueling. Not with swords, although I would not have put it past some of them, with equations. In Italy at this time you could challenge a mathematics professor to a public contest. If you solve more problems than him, you might get his job. So mathematicians kept their discoveries secret, the way a swordsman keeps his best move secret before a duel. A professor named Scipione del Ferro had figured out how to solve a particular type of cubic equation, an equation where the unknown is raised to the third power. On his deathbed, he passed the secret to his student Antonio Fiore. Fiore, full of confidence, challenged a self-taught mathematician named Niccolò Fontana, known as Tartaglia, which means the stutterer. Tartaglia had a rough childhood. He was slashed across the face by a French soldier as a boy, which left him with a speech impediment for life. But his mind was extraordinary. The night before the contest, working in a frenzy, Tartaglia independently rediscovered the solution to the cubic. He solved all 30 of Fiore's problems in about 2 hours. Fiore could not solve a single one of Tartaglia's. Now, the solution to the cubic was eventually published by another mathematician, Girolamo Cardano, and this is where things get truly interesting. When you applied the solution formula to certain cubic equations, you were forced, absolutely forced, to take the square root of negative numbers. What number multiplied by itself gives you -1? There is no such number, not among any numbers anybody had ever worked with. 3 times 3 is 9. -3 times -3 is also 9. Everything squared is positive. So the square root of -1 seemed like pure nonsense. Cardano called these quantities fictitious. He said working with them was mental torture. But another Italian, Raphael Bombelli, an engineer by training, had the courage to push forward. He said, in effect, I know these things look absurd. But if I just follow the algebra, if I treat the square root of -1 as though it were a number, and apply the ordinary rules, and carry it through the whole calculation, something remarkable happens. At the end, the fictional numbers cancel out, and you are left with a perfectly real, perfectly normal answer. Bombelli tried it. It worked. The answer to the cubic equation was 4, a number you could hold in your hand. But to get there, you had to pass through a strange land of impossible numbers, like a road that goes through a tunnel under a mountain. The tunnel does not look like it should be there, but it connects 2 real places. For about 300 years, that is how people treated these numbers. The great René Descartes gave them their name, imaginary numbers. He meant it dismissively. They were not real, they were a trick. Scaffolding, you put up during construction and tear down when the building is finished. Other mathematicians, like Euler and Gauss, developed the theory further. They showed that if you combine an ordinary number with an imaginary number, you get what is called a complex number, and complex numbers turned out to be incredibly useful in pure mathematics. What made many calculations easier, they had beautiful geometric properties. You could represent them as points on a plane, with the real part on one axis and the imaginary part on the other. They became a central tool of mathematics. But nobody thought they were physically real. They were a convenience, a shortcut. Even when engineers started using them to analyze electrical circuits, the attitude was the same. The imaginary part is just a mathematical trick. The real world runs on real numbers. Then along came the 20th century, and the scaffolding turned out to be the building. In 1925 and 1926, physicists were constructing a brand new theory of how atoms work, quantum mechanics. And right at the heart of it, in the equation Erwin Schrödinger wrote down to describe the behavior of an electron, there sat the imaginary number, the square root of -1, not as a trick, not as something that washes out at the end, The wave function, the central object of quantum theory, the thing that tells you everything there is to know about a particle, is fundamentally complex. It lives in the space of complex numbers. It has a real part and an imaginary part, and both parts are physically meaningful. Schrödinger hated this. He wrote to the physicist Hendrik Lorentz complaining that the use of complex numbers was objectionable. He tried to rewrite his equation using only real numbers. Others tried too. For decades, people attempted to reformulate quantum mechanics without imaginary numbers. And just recently, experiments have been done that appear to settle the matter. You cannot reproduce the predictions of quantum mechanics with real numbers alone. The imaginary numbers are not optional. They are not a human convenience. They are a feature of the theory that has no real number substitute. So let that soak in. A kind of number that was invented by Italian mathematicians in the 1500s to solve a puzzle about cubic equations. A number that Descartes called imaginary because it seemed to have no connection to physical reality, turned out to be essential, not optional, but essential, to describing how every atom in the universe behaves. The Italians were not thinking about atoms. They had no idea atoms existed. They were playing a mathematical game, and the game forced them to invent a new kind of number. And 3 centuries later, nature said, "Those numbers? I have been using them the whole time." How do you explain that? I am not asking you to explain it because I have a clever answer waiting. I am asking because I genuinely do not know. All right, that is layer 1. Let me add another. For over 2,000 years, all of geometry was Euclid's geometry. Flat geometry. The geometry of the tabletop, the chalkboard, the piece of paper. Euclid built his system on 5 postulates. Basic assumptions that seem self-evidently true. The first 4 were simple and uncontroversial. The 5th, the parallel postulate, was different. It says roughly that given a straight line and a point not on that line, there is exactly one line through that point that runs parallel to the first line. It sounds obvious, it looks obvious. For 2 millennia, nobody seriously doubted it. But it nagged at people. It was longer and more complicated than the other 4 postulates. Mathematicians kept trying to prove it from the other 4 to show it was not really an independent assumption but a consequence. Nobody could do it. And eventually in the 1800s, several mathematicians independently asked the truly radical question, what if it is wrong? What if there are no parallel lines, or infinitely many? What kind of geometry do you get then? This was not motivated by any physical observation. Nobody had looked at the sky and noticed that parallel lines were meeting. This was a question about the logical structure of mathematics itself. Pure curiosity, mathematical mischief, you might even say. In 1854, a young German named Bernhard Riemann, 27 years old, nervous, sickly, painfully shy, gave a lecture at the University of Göttingen. His examiner was the legendary Carl Friedrich Gauss, then 76 years old and widely considered the greatest mathematician alive. Riemann was so anxious he could barely speak, but the lecture he gave was one of the most important in the history of mathematics. Riemann laid out a completely new framework for geometry. Not just one alternative to Euclid, but an entire universe of possible geometries. He showed how to describe spaces of any number of dimensions, with curvature that could vary from point to point. In some regions, space might curve like the surface of a sphere. In others, it might curve like a saddle. The curvature could be gentle here and sharp there, and Riemann worked out the mathematics, the metric tensor, and what would later be called the Riemann curvature tensor, for measuring distances, angles, and shapes in these warped and bendy worlds. It was magnificent. It was also, as far as anyone could tell, completely useless. No physical application was known. No physical application was even imagined. Riemann was doing this because he found it mathematically interesting. Gauss, the old master, was apparently deeply moved by the lecture. He sat in silence for a while afterward, which for Gauss was the highest possible praise, but the work went into the mathematical literature where it sat, admired by specialists and ignored by everyone else. Riemann died of tuberculosis at the age of 39. He never knew what his geometry would become. He died thinking it was a beautiful piece of pure mathematics, admired by a few specialists, destined perhaps for the footnotes of mathematical history. He could not possibly have imagined that his abstract curved spaces would turn out to be the actual shape of the universe. 61 years later, in 1915, Albert Einstein published his general theory of relativity. He had this extraordinary, almost absurd idea: gravity is not a force. Gravity is the curvature of space and time. The presence of matter and energy warps the geometry of the universe itself, and objects moving through this warped geometry follow the straightest possible paths, which to us look like the curves of an orbit or the arc of a falling apple. The idea was clear in Einstein's mind, but he needed mathematics to express it. He needed a way to describe a four-dimensional curved space where the curvature changes from place to place depending on where the matter is. He struggled with this for years. It nearly broke him. And then his old university friend, the mathematician Marcel Grossman, said, "Albert, I think what you need already exists. A man named Riemann worked it out 60 years ago." Grossman introduced Einstein to Riemannian geometry, and it fit like a glove made before the hand existed. Every prediction of general relativity, the bending of starlight around the sun, confirmed by Eddington in 1919, the precession of Mercury's orbit, the expansion of the universe, the existence of black holes, the gravitational waves detected just recently, all of it, every last bit, flows from Riemann's abstract geometry applied to the structure of space and time. A shy mathematician playing with ideas about curved spaces in 1854, no physical motivation, no practical application in sight. And 60 years later, those ideas turn out to describe how the entire cosmos is built. Now let me show you the most dramatic case of all. In 1928, Paul Dirac, a very quiet, very peculiar Englishman at Cambridge, was trying to solve a specific technical problem. He wanted an equation for the electron that was consistent with both quantum mechanics and Einstein's special theory of relativity. The existing equations could handle one or the other, but not both at the same time. Dirac was not primarily an experimentalist. He was, in his bones, a mathematician. He once said something I find deeply revealing. He said, "A good deal of my work consists of playing with equations and listening to what they tell me. That is extraordinary." He is saying the equations speak, that if you set them up right, they have something to say that you did not put in. And the equation he found was breathtaking, the Dirac equation. It was more beautiful than what came before, simpler in a deep structural way, more symmetric. It automatically predicted the spin of the electron, a quantum mechanical property that earlier theories had to insert by hand, like taping an extra wheel onto a car. It got the magnetic properties right to remarkable precision. It unified quantum mechanics and special relativity in a single elegant expression. People recognized it immediately as something special. It had the unmistakable ring of truth. But it had a strange feature, like the equation x squared equals 4, which has two solutions, x equals 2 and x equals minus 2. The Dirac equation had two sets of solutions. One set described ordinary electrons with positive energy. The other set described a particle with the same mass as the electron but with a positive charge instead of negative. A mirror image particle. Nothing like it had ever been observed in any laboratory on Earth. Even Dirac hesitated. He tried to interpret these extra solutions as protons, the positively charged particles in the nucleus. But that did not work. The proton is nearly 2,000 times heavier than the electron, and the equation demanded a particle with exactly the electron's mass. So Dirac, with great reluctance and great courage, followed the mathematics. He published a paper predicting that there must exist a completely new form of matter, a kind of anti-electron that nobody had ever seen. Many physicists thought the equation had to be wrong. The idea of antimatter seemed too exotic, too speculative. It had no experimental support. It came from nothing but mathematics. Some people tried to find a way to throw out the negative energy solutions and keep only the positive ones. It could not be done cleanly. The equation was all of a piece. You could not take the parts you liked and discard the rest. The mathematics was insistent. In 1932, just 4 years later, the American physicist Carl Anderson was photographing cosmic rays with a cloud chamber at the California Institute of Technology. A cloud chamber is a beautiful device. Charged particles leave trails of tiny droplets as they pass through supersaturated vapor, like contrails written in miniature. Anderson set up a lead plate across the middle of the chamber and applied a magnetic field. The lead plate slowed down any particle that passed through it, and the magnetic field curved the particle's path, so by looking at the curve before and after the plate, you could figure out the mass and charge of the particle. Anderson photographed a particle that curved the wrong way. The curvature said it had the mass of an electron, almost exactly. But the direction of the curve said the charge was positive. He checked and rechecked. The trail was unmistakable. He had found the positron, the anti-electron, exactly what Dirac's equation had demanded. Think about what happened. A man sat down with pen and paper. He was not looking through a telescope. He was not smashing atoms in an accelerator. He was solving an equation, and the equation told him something existed that no experiment had ever hinted at, a new form of matter, a mirror image of the matter we are made of. And when someone finally looked in the right place with the right instrument, there it was, as real as a rock, as solid as a chair, but predicted first by nothing more than the internal logic of a mathematical equation. I want you to hold all these examples in your mind at once, because together they form a pattern, and the pattern is the real puzzle. Imaginary numbers invented for cubic equations, essential to quantum mechanics. Riemannian geometry invented for its own sake, essential to general relativity. The Dirac equation, written on mathematical grounds, predicting antimatter. And we have not even talked about Maxwell. James Clerk Maxwell, born in Edinburgh in 1831, is, I would argue, one of the greatest physicists who ever lived. Einstein had a picture of Maxwell on his study wall. That tells you something. In the 1860s, Maxwell brought together everything known about electricity and magnetism. The work of Faraday, Ampere, Coulomb, Gauss, and others. He unified it into 4 equations. Each equation summarizes a known fact. The first describes how electric charges create electric fields. The second says there are no isolated magnetic poles. The third, Faraday's law, says a changing magnetic field generates an electric field. And the fourth, Ampere's law, with Maxwell's own crucial correction, says a changing electric field generates a magnetic field. Now here is the thing. If a changing magnetic field creates an electric field and a changing electric field creates a magnetic field, then these two fields can sustain each other. They leapfrog through empty space, each generating the other. The equations predict a self-propagating wave of electromagnetic energy. Maxwell calculated the speed this wave should travel using 2 numbers measured in laboratories by people studying the static properties of magnets and charged objects. Numbers that had absolutely nothing to do with light. And the speed came out to approximately 300 million meters per second. The speed of light, Maxwell could scarcely believe it. He wrote that we can scarcely avoid the conclusion that light consists of the transverse undulations of the same medium responsible for electric and magnetic phenomena. In plain words, light is an electromagnetic wave. Nobody suspected this. Electricity, magnetism, and optics had been treated as completely separate subjects for centuries. And Maxwell's 4 equations said they were all the same phenomena. But the equations said more. They predicted electromagnetic waves at every wavelength, not just visible light. Waves much longer and much shorter than anything the eye can detect. Maxwell died in 1879, only 48 years old. In 1887, Heinrich Hertz built a simple apparatus in a laboratory in Germany, a spark gap on one side of the room and a loop of wire on the other, and detected radio waves jumping through empty space. Waves that had been hiding in 4 equations about magnets and wires. From those 4 equations eventually came radio, television, radar, wireless communication, and the entire infrastructure of the modern world. All of it was implicit in the mathematics, waiting to be extracted, like a symphony encoded in the marks on a page of sheet music that nobody had yet learned to read. And there is one more example I want to give you, because it illustrates the same principle from a completely different angle. In the middle of the 19th century, mathematicians developed a branch of abstract algebra called group theory. A group in mathematics is a set of objects with an operation that combines them, following certain rules. The rules are simple. There must be an identity element that does nothing. Every element must have an inverse, and the operation must be associative. That is it. Very abstract, very dry if you are not a mathematician. The theory was developed to study the symmetries of equations. The mathematician Évariste Galois, a young Frenchman who died in a duel at age 20, had used groups to prove that there is no general formula for solving equations of degree 5 or higher, the way there is for quadratics and cubics. It was a beautiful result in pure mathematics. Nobody imagined it had anything to do with the physical world. And then, in the 1920s and 30s, Eugene Wigner himself, the same Wigner who later wrote about the unreasonable effectiveness of mathematics, discovered that group theory was exactly what was needed to classify the behavior of atoms. The symmetries of quantum mechanical systems, the ways you can rotate or reflect or exchange particles without changing the physics, these symmetries form mathematical groups. And the properties of those groups determine what energy levels an atom can have, what transitions are allowed, what spectral lines you will see when you heat the atom up. Later, in the 1950s and 60s, group theory became even more central to physics. The classification of elementary particles, the quarks and leptons that make up all matter, is organized by group theory. The very structure of the standard model of particle physics, the most successful theory in the history of science, is built on something called gauge symmetry, which is a direct application of the mathematics of groups. Mathematicians playing with abstract symmetries in the 1800s built the scaffolding for a theory of matter that would not be written down for another 100 years. You see the pattern. It is not one coincidence. It is dozens of coincidences piled on top of each other in field after field, century after century. All right, so we have all these examples, and the question we cannot avoid is, why? Why does mathematics, a system we apparently invented for our own purposes to solve our own puzzles, keep turning out to be the language the universe is written in? Not just a useful approximation, not just a rough sketch, but the precise, exact, astonishingly accurate language. My colleague Eugene Wigner, a fine physicist at Princeton, gave a lecture about this in 1959 at New York University. He called it the unreasonable effectiveness of mathematics and the natural sciences. And the word he chose, unreasonable, was not casual. He was not saying mathematics is effective. Everybody knew it was effective. He was saying the effectiveness is more than we have any right to expect. It demands explanation, and we do not have one. Wigner told a charming little story to make his point. Two old friends from high school meet up years later. One has become a statistician studying population trends. He shows his friend a research paper full of equations. The friend peers at the formulas and says, "What is this symbol?" The statistician says, "That is pi." "What is pi?" "The ratio of the circumference of a circle to its diameter." And the friend says, "Now you are pulling my leg. Surely the population has nothing to do with the circumference of a circle." But it does. Pi appears in the formula for the Gaussian distribution, the famous bell curve, which describes how measurements of almost anything tend to cluster around an average value. And the bell curve is not limited to populations. It shows up in the distribution of errors in experiments, in the velocities of molecules in a gas, in the noise patterns in an electrical circuit, in the fluctuations of the stock market. A number defined entirely by the geometry of circles turns out to be essential to understanding randomness and probability. Nobody designed it that way, nobody expected it. The mathematics connects domains that on the surface have nothing in common, and it does it over and over again relentlessly as if it knows something we do not. Let me lay out the positions you can take on this question, because I think intellectual honesty requires it. Nobody knows the answer, I certainly do not, but there are reasonable things to say. The first position is that mathematics is not invented. It is discovered. The numbers and structures were always there, out in the world or in some abstract realm, and we stumbled upon them the way an explorer stumbles upon a river. On this view, it is not surprising that math describes the universe, because math is part of the universe. We did not create the number 7 any more than we created the Rocky Mountains. We found it. The trouble with this view is that it raises a haunting question. Where is the number 7? You cannot point to it. You cannot weigh it. If it exists independently of our minds, what kind of existence is that? Plato had an answer. He said there is a realm of perfect forms, and the things we see in the physical world are imperfect copies of those forms. The circle you draw on paper is a lousy approximation of the perfect circle that exists in the realm of forms. It is a grand idea, but it is very hard to test, and most modern scientists are uncomfortable with it. The second position is the opposite. Mathematics is entirely a human invention, and the reason it works in physics is selection bias. Over the centuries, mathematicians have produced an enormous amount of mathematics, thousands of different structures, geometries, algebras. Most of it has no known physical application. Once in a while, a piece of pure mathematics turns out to be useful in physics, and when that happens, we are amazed. But we are only looking at the hits and ignoring the misses. It is like a man who fires 1,000 arrows at a barn wall and then draws targets around the ones that stuck. There is something to this. It is true that a lot of mathematics has no known physical use. But I do not think the argument goes far enough, because when mathematics does apply to physics, it does not apply approximately. It applies exactly. Quantum electrodynamics, my own field, predicts the magnetic moment of the electron to an accuracy of about 1 part in 10 billion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. No theory in the history of science has ever been that precise, and the mathematics was not designed to be that precise. It just came out that way. Selection bias does not explain that kind of accuracy. The third position is that the universe has deep regularities, patterns, symmetries, and mathematics is simply the best tool for finding and describing patterns. If the universe were truly chaotic, truly random, with nothing repeating and no structure at any level, then mathematics would be useless. But the universe is not like that. The same law of gravity that governs an apple falling from a tree governs the motion of the planets and the collapse of a star. The same quantum mechanics that describes a hydrogen atom describes a superconductor. Nature reuses its laws. And mathematics, which is essentially the systematic study of patterns and structure in the abstract, is the natural tool for a patterned universe. I find this persuasive up to a point, but it pushes the question back one step. Why does the universe have deep patterns? Why are the laws of nature the same everywhere and at all times? That is not a logical necessity. You can imagine a universe where the rules change from place to place or from Tuesday to Wednesday. A universe where the force of gravity is a little different in the Andromeda Galaxy than it is here. Such a universe would be logically possible. It just would not be ours. So the question becomes, why this universe? Why one with patterns so deep and so exact that they can be captured in compact mathematical expressions? And let me push on this a little more, because there is another strange thing. It is not just that the universe has patterns, it is that the patterns are nested. The law of gravity that describes an apple falling from a tree is the same law that describes the moon going around the earth and the earth going around the sun, and the sun going around the center of the galaxy. One law applied at wildly different scales with wildly different objects gives correct results everywhere. Newton derived his law from, as Wigner put it, very scanty observations. A few falling objects, the orbit of the moon, some rough data about the planets. And from that slender evidence he extracted a law that turned out to work across the entire universe with an accuracy far beyond anything his data could have justified. Why should a law derived from watching apples fall in England work for predicting the orbit of a comet that will not return for 1,000 years? That is not selection bias. That is something else. That is something else. That is the universe cooperating with mathematics in a way that we do not understand. The fourth position, and this is the most radical one, is that the universe does not merely obey mathematical laws. The universe is a mathematical structure. The physical world literally is mathematics. This is an idea that some physicists have taken seriously. On this view, the mystery dissolves because there is no gap between math and nature. They are the same thing. I confess I am not sure I understand what this means. When someone tells me a rock is a mathematical structure, I want to pick up the rock and ask, where is the math? But I mention it because it shows how far people will go to grapple with this puzzle. Here is where I come down, and I want to be very careful because I have no proof, and neither does anyone else. I think mathematics is not just a language. It is a language plus reasoning. It is the most rigorous, most precise, most unforgiving system human beings have ever devised for drawing consequences from premises. You start with a few assumptions. You follow the logical rules and outcome conclusions you never anticipated. And the universe really does have structure. There really are symmetries and conservation laws and regularities, and these are features of nature, not of our minds. Mathematics, being the sharpest tool for detecting and expressing structure, finds that structure and finds it exactly when there is structure to be found. Math finds it. When there is no structure, math has nothing to say. But that still leaves the deep mystery. But why does mathematics develop for purely internal reasons like imaginary numbers or Riemannian geometry or group theory keep turning out to be exactly what physics needs? If math is just a tool for detecting the structure that is already there, why does inventing new mathematical structures for their own sake keep producing exactly the structures the universe turns out to use? I do not have an answer. Wigner did not have an answer. He called it a gift we neither understand nor deserve. I would not go quite that far, but I understand the impulse. Let me tell you one more thing before I close, something about how this mystery plays out in the daily work of a physicist, because it matters. When a physicist is searching for a new law, they are often guided not by experiment, not by data, but by mathematical beauty. They look for equations that are symmetric, economical, elegant. Dirac was explicit about this. He said he believed mathematical beauty was a more reliable guide to truth than experimental data. That is an extraordinary thing for a scientist to say. And yet, the historical record suggests he was not entirely wrong. The beautiful equation, the symmetric one, the one that makes a mathematician's heart beat a little faster, very often turns out to be the right one. Why should that be? Why should our sense of beauty have anything to do with the way the universe works? Well, just one answer is that the laws of nature really are simple, and simplicity looks like beauty when expressed in mathematical language. Not the phenomena. The phenomena are ferociously complicated. Weather, turbulence, life, consciousness, these things are complex beyond imagining, but the underlying rules from which all this complexity grows, those turn out to be quite compact. A handful of equations on a single page, and simple rules expressed precisely look beautiful. It is like music. The rules of harmony are fairly simple. A small number of principles about which notes work together and which clash. But from those simple rules, you get an infinite variety of music. Symphony, jazz, folk song, infinite variety from finite principles. Nature is like that. The variety of the world is without end. But the rules underneath might fit on a napkin. And I want to push this a little further because there is something else going on with mathematical beauty that I find deeply puzzling. When a physicist finds a beautiful equation, an equation with a certain elegance and economy, they tend to trust it even before the experiments confirm it. And this trust is not misplaced. The history of physics is full of cases where the more beautiful of two competing theories turned out to be the correct one. There is something about the aesthetic sense of a trained physicist that functions almost like a compass pointing toward truth. Now, why should that be? Why should the human brain, which evolved on the plains of Africa to avoid predators and find food, have an aesthetic sense that resonates with the fundamental laws of the cosmos? We did not evolve to do quantum mechanics. We did not evolve to understand curved space-time. We evolved to throw rocks and pick berries. And yet somehow the sense of beauty that we develop, perhaps because finding patterns helped us survive, that sense of beauty aligns with the deepest structure of reality. That too is part of the mystery. And here is the final thing that keeps me awake. Every time we write down the right equation, we find more in it than we put in. Maxwell put in electricity and magnetism. Out came light. Dirac put in the electron. Out came antimatter. Einstein put in the equivalence of gravity and acceleration. Out came the bending of space, the slowing of time, the expansion of the universe. In every case, the mathematics gives back more than it was given, as if, when we find the right equation, we have tapped into a vein that runs deeper than our original question. The equation knows things we do not. I have called mathematics a language plus reasoning, and by that I mean it is possible through mathematics to connect one statement to another, to chain inferences together, to arrive at places you never intended to go. And when those unexpected places turn out to be real, when you follow the chain of mathematics and end up at antimatter or gravitational waves or radio waves, that is when you feel the eerie chill that Wigner was talking about. That is when you suspect that something deeper than human cleverness is at work. I do not know why the universe is mathematical. I am not sure I know what it means to say the universe is mathematical. What I do know is that every time we have found a deep truth about nature, that truth has been expressible in mathematical form. And the mathematical form has always contained more truth than we put into it. Whether that is because mathematics is the language of nature, or because mathematics is the structure of nature, or because our minds are somehow tuned to the same deep frequencies as the cosmos, I cannot say. It remains one of the great open questions. Maybe the greatest, and it is wonderful that it is open because it means there is still something fundamental that we do not understand. And in my experience, the things we do not understand are always more interesting than the things we do. I want to close with one more look at where we started. 2 + 2 = 4. A fact so obvious that no child would question it. And yet, somehow that fact and everything it connects to, the whole vast, intricate, beautiful architecture of mathematics, all of it appears to be woven into the fabric of reality at the deepest level we can probe. We invented a game, and the universe was already playing it. Or maybe the universe invented the game, and we are just learning the rules. Or maybe there is no difference between those two statements. I do not know. But I find it wonderful that I do not know, because that means there is still something worth discovering. So here is what I want from you. What do you think? Is mathematics something we made up, something we found, or is it something else entirely? something we do not even have a name for yet. Think about it carefully, because whatever the answer turns out to be, it will tell us something very deep about what kind of universe we are living in.